The moon is about 240,000 miles away, and getting there is already one of the most dangerous things a human being can do. 12 people have stood on its surface. Every one of them rode a controlled explosion out of Earth's atmosphere, crossed 250,000 miles of vacuum, and came back in a heat shield moving faster than a bullet. The moon is our nearest neighbor. It is practically in our backyard, and it almost killed us several times. Now consider what lies beyond it. Space doesn't just get bigger as you move outward. It gets stranger. It gets more hostile in ways that compound with every added layer of distance, and the hostility is not random. It scales. The further you push from Earth, the more the physics of the universe reveal themselves in forms that have no parallel in anything a human being has ever experienced on the surface of this planet. There is no weather analogy, no ocean depth comparison that fully captures what waits past a certain threshold. Some of what exists out there operates by rules that only became known to science within the last century, and understanding those rules is not reassuring. Think of it as a series of shells. The innermost shell is familiar, low Earth orbit, where the International Space Station circles at roughly 250 miles up, sits inside Earth's magnetic field. That field is doing something extraordinary and invisible. It is deflecting a constant storm of charged particles streaming in from the sun and from deep space, bending them away from us before they can reach the surface. Astronauts aboard the station are still inside that bubble. They receive elevated radiation compared to people on the ground, but nothing catastrophic. They come home. The bubble holds. If you find comfort in these gentle explorations of space and science, I'd be grateful if you'd consider subscribing and giving this video a like. I'd love to know where you're watching from and what time it is for you. Feel free to drop your location and time in the comments below. Cross beyond the bubble, and the first rules change. Move out past the moon, out toward Mars, out into the space between planets, and you are exposed to the raw particle environment of the solar system, with nothing between you and it. Galactic cosmic rays, particles accelerated to near the speed of light by supernovae and other violent events scattered across the galaxy, stream through that space constantly. They pass through spacecraft walls. They pass through human tissue. The damage accumulates in ways that don't fully repair, and the further you go, the longer the exposure. That's just the background radiation. The sun can also produce sudden, unpredictable bursts of particles that spike the radiation environment to levels a human being cannot survive without heavy shielding. There is no reliable warning system. There is no shelter you can reach in time. That is only the first layer. There are 14 more before we're finished. The outer planets sit at distances between 4 and 30 astronomical units from the Sun, where an astronomical unit is the distance from Earth to the Sun, about 93 million miles. Push past them and you reach interstellar space, the territory between star systems, where the Sun's influence fades entirely and the full hostility of the galaxy asserts itself. Beyond that, the objects that exist, the things the universe has assembled over 13.8 billion years, begin to strain the vocabulary available to describe them. Neutron stars where a single teaspoon of material weighs 1 billion tons. Magnetars with magnetic fields so powerful they disrupt chemistry at a distance. Black holes where space and time bend so severely that the concept of escape becomes geometrically meaningless. Explosions that release more energy in seconds than the sun will produce across its entire lifetime. None of this requires imagination. These are measured, confirmed, catalogued objects. The universe contains them in enormous numbers, and they are not evenly distributed. They are out there, in the same galaxy we occupy, following the same orbital paths as everything else. What this video is going to do is take you outward, layer by layer, from the edge of Earth's protection into the deep structure of the cosmos, showing you exactly where things start going wrong, and how wrong they get. Some of it is a physics problem, some of it is a timescale problem, some of it is a problem with no solution currently known to science. The further out you go, the more the universe stops behaving like something you were meant to survive in. Earth's magnetic field is so ordinary to us that most people go their entire lives without thinking about it once. It doesn't glow. It doesn't make a sound. You can't feel it standing in a field or swimming in the ocean. It is simply there, wrapping the entire planet in an invisible cocoon generated by the churning of molten iron deep in Earth's core. And that invisible cocoon is the reason anything biological exists on this planet at all. Without it, the surface of Earth would be bathed in radiation intense enough to unravel the molecular machinery of living cells. Life as we know it would not have had the chance to get started. The magnetosphere is not a convenience. It is a prerequisite. Here is what it actually does. The sun continuously fires a stream of charged particles outward in every direction. This is the solar wind. Protons, electrons, and heavier ions moving at hundreds of kilometers per second. A constant invisible river, washing over everything in the solar system. When those particles reach Earth, most of them don't hit the surface. The magnetic field deflects them, bending their paths around the planet like water splitting around a stone. Some get funneled into the polar regions, where they interact with the upper atmosphere and produce auroras. Most just continue outward, missing Earth entirely. The planet is, in this sense, hiding behind its own magnetic field every single day. Astronauts in low Earth orbits sit inside this bubble. The International Space Station orbits at roughly 400 kilometers altitude, well within the magnetosphere's protection. Crew members still accumulate more radiation than people on the ground. The shielding is imperfect and thin at orbital altitudes, and certain high-energy particles slip through. But the exposure levels are manageable. Astronauts on long-duration station missions receive careful monitoring and stay within calculated lifetime limits. The system works more or less within that protected zone. The moment a spacecraft climbs higher and crosses the magnetosphere's outer boundary, the situation changes in a way that is not gradual. It is immediate, and the numbers shift dramatically. What waits outside is not simply more solar wind. The deeper threat is something called galactic cosmic rays. These are not particles coming from the sun. They come from everywhere. They are generated by violent events scattered across the galaxy. Supernovae, neutron star collisions, the jets of feeding black holes, and they have been accelerating through interstellar space, sometimes for millions of years, building up energies that are difficult to express in ordinary terms. By the time they reach our solar system, some of them are traveling at very close to the speed of light. They carry energies millions of times higher than anything produced by medical imaging equipment. A dental X-ray deposits its energy in tissue and stops. Galactic cosmic rays don't stop. They punch through the walls of spacecraft as though the metal isn't there. They punch through human tissue the same way. And as they pass through, they break things. The damage they do at the cellular level is specific and serious. When a high-energy particle tracks through a strand of DNA, It doesn't cause a single clean break that cellular repair mechanisms can easily fix. It causes complex, clustered damage, multiple breaks close together, modifications to the base pairs, crosslinks between strands. Cells have repair systems for DNA damage, but those systems were shaped by evolution to handle the kinds of damage that happen on Earth's surface. Galactic cosmic rays produce damage patterns that those repair systems struggle with. Some of the damage gets fixed incorrectly. Some doesn't get fixed at all. Over weeks and months, the errors accumulate. The long-term consequences are not hypothetical. Researchers have studied radiation exposure in astronauts and in animal models placed in simulated deep space radiation environments. What they've found is a consistent pattern of elevated cancer risk, not just common cancers, but aggressive and rare types as well. A mission to Mars, which would take somewhere between 7 and 9 months each way depending on orbital timing, would expose the crew to radiation doses that push significantly beyond the limits currently defined as acceptable for professional astronauts. Both the journey there and the return, plus the surface stay, add up to a cumulative dose that raises lifetime cancer risk in ways the numbers make hard to ignore. Cancer is not the only concern. Galactic cosmic rays also pass through the brain, and the damage they do there is different from the damage that ionizing radiation typically causes in neural tissue. Studies on mice exposed to the specific particle types found in deep space showed something troubling. The animals developed measurable impairments in memory and cognition. They had difficulty with spatial reasoning and problem-solving tasks they previously managed easily. Inflammation in brain tissue persisted well after the exposure ended. NASA researchers began referring to this effect with a name that makes it sound almost benign: space brain. But what it describes is cognitive decline, degraded judgment, impaired memory, reduced ability to think clearly, occurring in crew members who need to be operating at full capacity during one of the most complex and dangerous missions in human history. Then there is the solar particle event problem. Galactic cosmic rays are a chronic background threat. Solar particle events are something different. They are acute. Without reliable warning, the sun can fire off a massive burst of energetic particles, a coronal mass ejection or a solar proton event that sweeps outward through the solar system at enormous speed. On Earth, the magnetosphere handles this. On a spacecraft between Earth and Mars, there is nothing to deflect it. The radiation levels during a major solar particle event can spike to potentially lethal doses in a matter of hours. An astronaut caught outside the spacecraft during one on a spacewalk for maintenance or repair could absorb a fatal dose before returning inside. The shielding inside the spacecraft itself reduces exposure but does not eliminate it for the most intense events on record. What makes this particularly difficult is the warning problem. Solar particle events can sometimes be predicted hours in advance based on observations of solar activity, but not always. The gap between the first signs and the arrival of dangerous radiation can be short. A major event can build faster than models anticipate. There is no shelter on the route to Mars that is not already the spacecraft. If the shielding is insufficient for the event that arrives, there is no backup option within range. Mission designers have spent years working on this problem, exploring water walls, polyethylene shielding, storm shelters built into the center of spacecraft using dense materials as a barrier. Every solution involves trade-offs with weight, with cost, with the geometry of what a spacecraft can carry. Nothing currently designed provides the kind of protection the magnetosphere delivers for free. This is worth sitting with for a moment. Every person alive is standing inside a planetary magnetic field that makes biological existence viable, and almost none of them are thinking about it. The field is not static. It has weakened and shifted and even reversed polarity over geological time. But right now it is doing its job, silently, continuously, deflecting a particle environment that would otherwise be incompatible with the human body on long timescales. The astronauts who walked on the moon in the late 1960s and early 1970s were outside this protection for around 8 to 12 days. They got lucky with solar activity. No major particle event occurred during any of those missions. A mission to Mars stretches that exposure window to roughly 18 months or more from departure to return. The probability of encountering nothing significant over that span is not high, and the consequences of encountering something significant at the wrong moment are not recoverable. The magnetosphere is not just a shield, it is an address. It marks the boundary between the part of the solar system where human biology can survive with careful management and the part where the universe is actively working against it at the atomic level. Outside the magnetosphere, every hour spent in transit is an hour being slowly dismantled from the inside out. Most people imagine space as cold, and that is true. But the way it is true is stranger than the word cold suggests. Cold implies a temperature, something measurable, something a thermometer can handle. What space offers in its shadowed regions, the vast stretches between objects where no sunlight reaches, is a temperature of around -270 degrees Celsius. That is 3 degrees above absolute zero. Absolute zero is not simply very cold. It is the point at which molecular motion effectively stops. There is no lower bound. You cannot go further down. The shadowed vacuum of deep space sits just barely above that floor, and it has been sitting there for billions of years. But here is what makes the thermal reality of space genuinely strange. That same environment, exposed to direct sunlight with no atmosphere to diffuse or scatter the radiation, can reach temperatures above 120 degrees Celsius on a surface in full sun. A spacecraft in orbit is simultaneously managing surfaces that face the sun and surfaces turned away from it, with temperature differences of 200 to 300 degrees across its own hull. The engineering required to prevent a vehicle from cracking apart under that stress is not trivial. There are no seasons in space, no weather, no gradual transitions. One side of a metal panel is searing. The other side is approaching absolute zero. The spacecraft sits in the middle of this, trying not to fail. This is already hostile, but the vacuum itself is a separate problem, and it is the one that matters most for a human body. Most people's mental image of what happens when a person is exposed to open space comes from movies. The body inflates, the eyes bulge, there is an explosion of some kind. None of that is accurate. The real version is quieter, faster, and in most ways harder to watch. When pressure drops to near zero, the first thing that happens is that any air in the lungs tries to escape. If a person holds their breath, the expanding gas tears lung tissue. The correct instinct is counterintuitive. Exhale. But even if you do everything right, you have roughly 10 to 15 seconds of useful consciousness. Nitrogen that was dissolved harmlessly in the blood under normal pressure begins coming out of solution in the form of bubbles. The same mechanism as decompression sickness in divers, but happening across the entire circulatory system at once. The moisture on the surface of the eyes begins to evaporate. The saliva on the tongue does the same. The skin swells as water in the tissues vaporizes under the pressure differential. None of these processes are explosive. The body does not burst, but what happens is still catastrophic, and it happens quickly. 15 seconds. That is roughly what the physiology suggests for functional consciousness. After that, the process continues, but the person experiencing it is not aware of it. The body becomes an object rather than a person. In a vacuum, without heat exchange through convection or conduction, it would cool only through radiation, very slowly. A body in open space does not freeze instantly the way fiction suggests. It cools over hours. What this means practically is that the margin for error in any spacewalk, any suit malfunction, any breach in a spacecraft hull is measured in seconds. The equipment keeping a person alive in deep space is a thin layer of engineered material between a functioning human being and a process that renders them unconscious in the time it takes to say a sentence. Engineers who design spacesuits understand this. They think about failure modes in extraordinary detail. A pinhole leak in a glove, a seal that doesn't seat correctly, a micrometeorite moving at 10 kilometers per second. Any of these are enough. And as missions push further from Earth, the ability to respond to any of this diminishes. On the International Space Station, a medical emergency can result in an emergency return to Earth in a matter of hours. The station sits in low Earth orbit. Distance is not the obstacle, but a crew on a transit to Mars is not hours from home. Depending on the orbital positions of the planets, the journey takes somewhere between 6 and 9 months. A crew halfway through that transit is tens of millions of kilometers from the nearest hospital, the nearest surgeon, the nearest anything that could intervene. Radio signals travel at the speed of light. From Mars, at its farthest point from Earth, a signal takes around 20 minutes to arrive. A two-way conversation has a minimum delay of 40 minutes. You speak. 40 minutes later, you hear the response. In a crisis where a crew member is losing blood pressure, running a fever of unknown origin, or showing symptoms of a cardiac event, 40 minutes is not a communication inconvenience. It is the entire difference between an intervention and a retrospective analysis. Mission Control can watch data in near real time and send words back. They cannot send hands. They cannot send equipment that wasn't already on the spacecraft when it left. Every supply, every drug, every surgical instrument that crew might need has to have been anticipated months in advance and packed before departure. This is what compounds the thermal and vacuum threats. Each of these risks, the hull integrity, the suit systems, the cold, the pressure, is manageable in principle with enough support. The support exists on Earth. The support exists, to a reduced extent, in low Earth orbit. The further out a mission goes, the further it gets from any meaningful backup. The distance doesn't just make things harder logistically. It removes options that people on the surface take completely for granted. A surgeon developing appendicitis on a Mars transit has to be operated on by a crewmate following instructions from Earth with a 40-minute delay per message. That situation has been studied. NASA has procedures for it. The procedures are thorough. But there is no version of that scenario that is not deeply alarming, because the physics of the situation, the speed of light, the vacuum outside the hull, the thermal extremes pressing on every surface, do not bend for the inconvenience of the emergency. The cold and the vacuum are the most basic features of the environment beyond Earth. They precede every other danger covered in this journey outward. They are the flaw. Everything else stacks on top of them. And the further a mission goes, the more those baseline realities become the defining context for every decision made aboard. At a certain distance from Earth, any crisis you face is yours alone, because the speed of light will not let anyone help you in time. When a massive star exhausts its nuclear fuel and collapses, the outer layers bounce off the core and explode outward as a supernova. What remains after that explosion is not nothing. It is not empty space. What remains is the compressed heart of a dead star, and it is one of the strangest objects physics permits to exist. Astronomers call it a neutron star, and if everything described so far about radiation and vacuum and cold represents the dangers of the space between familiar things, then a neutron star represents something different. It represents matter itself pushed past the point of recognition. The rules that govern ordinary objects, the rules that hold atoms together, that give solids their solidity and liquids their weight, those rules stop applying here. A neutron star is a place where physics has been pushed so far past its comfortable range that the equations governing it are still partially contested. Here is the basic picture. A neutron star packs more mass than our entire sun into a sphere roughly 20 kilometers across. 20 kilometers. That is smaller than many cities. If you placed a neutron star where Chicago sits, it would fit inside the city limits with room to spare, and yet it would outweigh every planet in the solar system combined. The density involved is not something human intuition handles well, so consider this. A single teaspoon of neutron star material, if you could somehow transport it to Earth, would weigh approximately 1 billion tons. Not 1 billion pounds, 1 billion tons. The entire human population of Earth, all 8 billion people, weighs roughly 500 million tons together. 1 teaspoon of this object outweighs us all. The reason for this comes down to what a neutron star actually is. In ordinary matter, atoms are mostly empty space. The nucleus is tiny compared to the electron cloud surrounding it. When a stellar core collapses under gravity intense enough, that empty space is eliminated. Electrons are forced into protons, creating neutrons, and those neutrons are packed shoulder to shoulder with essentially no gap between them. The result is a single object with the density of an atomic nucleus, sustained at a scale of kilometers. The surface gravity of a neutron star runs to roughly 200 billion times what you experience standing on Earth. This number is difficult to make meaningful. On Earth, if you drop something, it accelerates at about 9.8 meters per second. An object falling from 1 meter above the surface would hit it moving at roughly 2,000 kilometers per second. But you would never reach the surface because the tidal forces would end you long before gravity had the chance to finish the job. Tidal forces are the difference in gravitational pull between one side of an object and the other. On Earth, the moon's tidal force on your body is so small it is completely unfelt. Near a neutron star, those gradients become lethal at enormous distances. The gravity varies so sharply across even a short distance that the pull on your feet and the pull on your head would differ by millions of times the force of Earth's gravity. Your body would not be compressed or burned. It would be stretched, lengthened along the radial direction, pulled apart atom by atom in the direction of the star before anything else could happen. This occurs not at the surface. It occurs hundreds of kilometers away, in open space, while the star is still a distant point in the dark. There is no threshold you cross where things become dangerous. The process begins gradually and then accelerates catastrophically and there is no distance from which a human body could approach a neutron star and remain intact. Not all neutron stars sit quietly. Many of them spin. When a stellar core collapses from something the size of the sun down to something the size of a city, it conserves its angular momentum, the same way a spinning skater pulls her arms in and spins faster. The result is a neutron star that can rotate at extraordinary rates. Some newly formed neutron stars spin dozens of times per second. The fastest known examples, called millisecond pulsars, complete several hundred full rotations every second. These are not slow celestial cycles measured in years or days. These are objects the mass of a star spinning faster than a kitchen blender. As a neutron star spins, its powerful magnetic field channels radiation into two narrow beams that sweep across space with every rotation. From a distance, this looks like a regular pulse of radio waves or X-rays arriving with extraordinary clockwork regularity. These are pulsars, and when astronomers first detected them in 1967, the signals were so precise and so regular that the researchers briefly considered the possibility that they were artificial. Nothing in nature, they assumed, produced signals that clean. They were wrong. Nature produces them routinely, and the regularity comes from the same physics that makes a lighthouse beam predictable: a fixed rotation rate, a fixed geometry, and nothing to interrupt the sweep. Some pulsars keep time well enough to rival atomic clocks over spans of years. The regularity is a feature of the physics, not a sign of intelligence behind it. If you were close enough to a pulsar to study it directly, the radiation sweeping past you with every rotation would be lethal. The beam itself carries enormous energy, and depending on the pulsar's type and spin rate, proximity would mean exposure to X-ray and gamma-ray pulses arriving hundreds of times per second, each one carrying energy densities that would overwhelm any shielding currently conceivable. The radiation environment around an active pulsar is not survivable. The question is only how far away lethal exposure begins, and for the most energetic pulsars, the answer is measured in light years rather than kilometers. Then there are the starquakes. A neutron star is not perfectly smooth. Its outer layer is a solid crust, and despite the unimaginable pressure bearing down on it from above and below, that crust can crack. As a neutron star slowly cools over millions of years, it contracts slightly. The crust, rigid and crystalline, does not shrink smoothly. It holds its shape until the internal stress overwhelms it, and then it fractures. The energy released in that fracture does not travel through rock and soil the way an earthquake does. It propagates through the most dense material in the universe, and then radiates outward as a burst of X-rays and gamma rays powerful enough to register on detectors here on Earth, even from tens of thousands of light years away. The largest starquakes ever recorded released more energy in a fraction of a second than the Sun emits over an entire decade. One event in 2004, from an object roughly 50,000 light years from Earth, briefly overwhelmed satellite detectors and produced measurable effects on the Earth's upper atmosphere from that distance. These events are not exotic theoretical possibilities. They happen. They have been observed. They are what a neutron star does when its crust can no longer hold. What makes neutron stars philosophically unsettling, beyond the numbers themselves, is what they represent about the limits of our understanding. The physics of the outer crust, where densities are merely extreme, is reasonably well described, but the interior, where pressure climbs still higher, enters a regime where the behavior of matter is genuinely unknown. Some models suggest the core may contain exotic particle states that have never been observed or created in any laboratory on Earth. Others propose still stranger configurations. The honest answer is that we do not know what the center of a neutron star is made of, because no experiment we have ever run or could run in a terrestrial setting comes anywhere near the relevant conditions. These objects exist at the boundary of known physics, and every equation we apply to them is an extrapolation from conditions far less extreme. The core it leaves behind is something no instrument we have ever built could survive examining at close range. Among neutron stars, there is a subset so extreme that they make ordinary neutron stars seem almost approachable by comparison. A neutron star, as established, is already one of the most extreme objects in the observable universe. Its density defies analogy. Its gravity would kill a human being long before the surface became visible. And yet, there exists a class of neutron star that takes everything extreme about those objects and amplifies it by a factor that stops being a number and starts being a concept. These are magnetars, and the thing that separates them from ordinary neutron stars is their magnetic field. To understand what a magnetar's magnetic field actually means, you need a reference point. The strongest MRI machines built by human beings generate magnetic fields of around 10 Tesla. That is already powerful enough to pull metal objects across a room, to interfere with electronic equipment, and to require careful protocols around anyone with metallic implants. Hospital MRI suites are engineered specifically to contain and manage that level of field strength. A typical neutron star generates a magnetic field of roughly 100 billion Tesla. That number already exceeds anything achievable in a laboratory by such a margin that direct comparison loses meaning. A magnetar's field is approximately 1,000 times stronger still, reaching somewhere around 100 trillion Tesla. The strongest magnetic force known to exist in the universe, and it is carried by an object roughly the size of a city. The consequences of a field that powerful are not just quantitatively different from anything else, they are qualitatively different. Physics starts behaving in ways that have no counterpart anywhere in ordinary experience. At a distance of 1,000 kilometers from a magnetar, the magnetic field would be strong enough to distort the electron clouds surrounding individual atoms. Electrons do not simply orbit nuclei at fixed distances. They exist in probability clouds, quantum structures that define the shape and behavior of every chemical bond that has ever formed anywhere. A magnetar's field at that distance would deform those clouds. Chemistry itself, the entire architecture of molecular interaction, would stop functioning normally. Biological molecules, the proteins and nucleic acids that make life possible, would not hold together. Not because of heat, not because of radiation, but because the magnetic field would physically prevent the electron behavior that chemical bonding depends on. At 1,000 kilometers, the problem is not survival. It is that the atoms making up any living thing would cease to be organized in the way that distinguishes living matter from scattered particles. This is worth holding for a moment. The Sun is about 1.4 million kilometers in diameter. The distance at which a magnetar destroys chemistry is 1,000 kilometers. These are not comparable scales. You would need to be extraordinarily, almost inconceivably close to a magnetar for its field to do this. But the fact that such a physical threshold exists at all The fact that there is a distance from a single object in the universe where the rules governing molecular structure simply stop applying suggests something about how far outside ordinary physics these objects sit. The magnetic field is the foundation. What magnetars do with it is where things become genuinely alarming. Magnetars are not static objects. They are active, and their activity expresses itself in violent outbursts that release energy on scales difficult to contextualize. Two categories describe the bursting behavior astronomers observe. Soft gamma-ray repeaters are magnetars that emit irregular, unpredictable bursts of gamma rays and X-rays at intervals that cannot be forecast. Anomalous X-ray pulsars are magnetars emitting X-ray radiation at puzzlingly high levels, too bright to be explained by simple rotation alone. Both terms sound clinical. The phenomena they describe are not. A magnetar flare at its most extreme can outshine an entire galaxy for a fraction of a second. A galaxy containing hundreds of billions of stars. More light than those hundreds of billions of stars produce combined, concentrated into a burst lasting less than a second from a single object 20 kilometers across. The energy output during that moment exceeds what the sun will emit across its entire 10 billion year lifetime. This happens unpredictably, with no reliable precursor signal, from objects distributed across our galaxy. On December 27, 2004, one of those objects erupted. The magnetar designated SGR 18806-20 released a giant flare. In about 1/10 of a second, it emitted more energy than the sun produces in 250,000 years. The event saturated detectors aboard multiple spacecraft. Instruments designed to monitor gamma-ray sources from across the observable universe were simply overwhelmed. The burst was intense enough to ionize the upper layers of Earth's atmosphere. It measurably altered the ionosphere, the electrically charged region between roughly 60 and 1,000 kilometers altitude that radio waves rely on for long-distance transmission. Earth's own magnetic field and the full thickness of its atmosphere absorbed the impact, and the ionosphere still rang like a bell. SGR 1806-20 is approximately 50,000 light-years away. It sits on the far side of the Milky Way. The energy that disturbed Earth's ionosphere had been spreading outward through space for 50,000 years by the time it arrived. It had dispersed across a sphere 50,000 light-years in radius before it got here. What reached Earth was the faintest possible remnant of that event, and it still left a detectable mark on our planet. If that same flare had originated within a few light-years of Earth, the outcome would not have been a measurable ionospheric disturbance. The gamma radiation would have overwhelmed the magnetosphere, interacted catastrophically with the upper atmosphere, and driven ozone destruction on a global scale. The surface would have been exposed to radiation levels incompatible with complex life. A magnetar flare at stellar proximity is not a survivable event for a biosphere. The 2004 flare was far enough away that it became an interesting scientific observation. Move the source a few hundred times closer, and the same event ends the discussion. What makes this genuinely unsettling is not some abstract worst-case scenario built from hypothetical conditions. A magnetar went off in our own galaxy in 2004, and the effect was measurable on Earth from across the full diameter of the Milky Way. The object was not in some distant, unreachable part of the universe. It was here, in the same galaxy, subject to the same distribution of stars and stellar remnants that everything else in the Milky Way is subject to. The 50,000 light-year distance was not guaranteed. It happened to be that distance. Other magnetars are not at the same remove. Magnetars form from the same supernovae that produce ordinary neutron stars. The precise conditions that produce a magnetar rather than a standard pulsar are still not fully understood. Leading models suggest it has to do with the rotation rate of the collapsing core during the supernova, or with convective processes during collapse that amplify the magnetic field through something analogous to a dynamo effect. What is clear is that the outcome is not predictable from the outside. Massive stars that collapse into neutron stars may or may not produce magnetars, and there is no obvious external sign beforehand that distinguishes the progenitor stars. After formation, a magnetar's magnetic field does not persist indefinitely. The field decays on timescales of roughly 10,000 years. As it decays, the magnetar loses the energy source that powers its extreme activity. It quiets. Over longer timescales, it becomes, essentially, a standard neutron star. The window during which a magnetar is active and capable of producing catastrophic flares is geologically brief. In the full span of a galaxy's history, 10,000 years is nothing. But the Milky Way is old enough and has produced enough massive stars that at any given moment there will be some number of magnetars in their active phase somewhere within it. Astronomers identify magnetars by their outbursts. A quiescent magnetar, one between major flares, is virtually indistinguishable from the general background of the galaxy. It emits no particular signal that would flag its presence at a distance. The catalogue of known magnetars exists because those objects erupted at a moment when instruments were pointed in roughly the right direction. There are roughly 30 known magnetars in the Milky Way, and finding new ones requires them to do something violent first. A black hole is not a thing in the way that a star or a planet is a thing. A star is a ball of plasma held together by its own gravity. A planet is a mass of rock and metal with a definable surface. A black hole is a region of space-time where geometry itself has broken down. There is no surface to land on, no object to point a telescope at, no boundary you could touch. What exists at the center is called a singularity, a point where the equations of physics produce answers like infinite density and infinite curvature. Physicists generally interpret that as a sign that the equations have stopped working, not that infinity is actually there. The honest answer is that nobody knows what is at the center of a black hole. This was because nothing that has ever gotten close enough to find out has been able to report back. What makes a black hole detectable from the outside is its effect on everything around it. Gravity bends light. Near a massive enough object, that bending becomes extreme. Photons passing close to a black hole follow curved paths. At a specific radius called the photon sphere, they can actually orbit. If you could hover at exactly that distance, you could look straight ahead and see the back of your own head. This was because light from behind you would have curved all the way around and returned to your eyes. This is not a thought experiment, it is geometry. The mass is real, the curvature is real. The photon sphere around a stellar mass black hole sits at a distance of only a few kilometers from the center. The event horizon is further out than the photon sphere. It is the boundary most people have heard of. It is not a wall, it is not a surface. Cross it, and nothing about the immediate environment tells you something has changed. There is no membrane, no flash of light, no alarm. The event horizon is a geometric point of no return, the radius at which escape velocity exactly equals the speed of light. Inside that radius, every direction you could point a spacecraft, every path through space-time, curves inward. You are not being pulled toward the singularity in the way that gravity pulls a rock toward the ground. You are falling toward it the way time falls toward tomorrow. There is no engine in the universe powerful enough to reverse that direction. This was because the direction itself has been replaced. The environment approaching a black hole from the outside is something else entirely. Isolated black holes with no nearby gas or companion star are dark and effectively invisible. But most black holes we can actually observe have material falling into them. That material tells a story. As gas and dust spiral inward, they form an accretion disk, a flattened ring of superheated plasma swirling around the event horizon. The friction and compression in this disk push temperatures into the tens of millions of degrees. At those temperatures, the disk glows not in visible light but in X-rays, flooding the surrounding space with radiation lethal to anything biological within enormous distances. Some black holes produce something even more dramatic: relativistic jets, narrow beams of plasma that fire outward from the poles at close to the speed of light, extending for thousands of light years into surrounding space. The mechanism behind these jets is still not fully understood. What is understood is that they represent some of the most energetic, continuous processes in the observable universe. We have now detected these signatures across the universe. Radio telescopes have imaged the shadows of black holes themselves. The Event Horizon Telescope captured the first direct image of the black hole at the center of the galaxy M87, revealing a dark circle surrounded by glowing material. The detection methods vary. Some black holes are found through the X-ray emissions of their accretion disks, others through gravitational lensing that bends light from distant objects, and still others through the orbital motion of companion stars that circle them. In 2015, the Laser Interferometer Gravitational Wave Observatory detected the collision of two black holes by measuring the ripples in space-time itself that their merger produced. This opened an entirely new way of observing objects we cannot see directly. Black holes are no longer invisible in principle. They announce themselves through their effects on the universe around them. Now consider what happens if an object, a spacecraft, a person, anything with physical extent, approaches a stellar mass black hole. These are the black holes formed from the collapse of individual massive stars, typically ranging from a few to a few dozen solar masses. They are compact. Their event horizons sit at radii of a few kilometers, and because they are so compact, their gravitational gradient is extremely steep. This is the condition that produces spaghettification. Tidal forces exist wherever gravity is uneven across an object. The Moon produces tidal forces on Earth. The side of Earth facing the Moon is pulled slightly harder than the side facing away. That is why oceans bulge on both sides. Near a stellar mass black hole, this effect becomes catastrophic long before the event horizon. The gravitational pull on the near side of any object is vastly stronger than on the far side. That differential force stretches the object lengthwise and compresses it laterally. For a human body falling feet first toward a stellar mass black hole, the force pulling your feet toward the singularity would exceed the force pulling your head by hundreds of millions of times your body weight before you came anywhere near the horizon. The stretching would not be gradual, it would be instantaneous and absolute. Individual atoms in your feet would be accelerating faster than atoms in your head. At some point, that difference is enough to overcome every molecular bond in your body. You would be drawn out into a thin stream of particles, not dramatically, not slowly, but in a fraction of a second, while the event horizon was still thousands of kilometers away. The situation is different for supermassive black holes. The ones sitting at the centers of large galaxies, with masses of millions or billions of suns, have event horizons at radii of millions of kilometers. The gravitational gradient across a human-sized object at that distance is gentle enough that spaghettification has not yet occurred when the horizon is crossed. A person falling into a supermassive black hole would cross the event horizon without any immediate physical sensation of having done so. The radiation environment would be lethal. The tidal forces would eventually become fatal deeper inside, but the geometric boundary itself would pass without announcement. This is in some ways the more disturbing scenario. You would be inside a black hole, falling toward a singularity with absolute certainty, with no possible path of escape, without having felt the moment everything changed. The very mechanism that makes supermassive black holes safer to cross, their gentle gradient at the event horizon, is also what makes them most inescapable. You slip past the threshold of no return, not with violence but with indifference, and only later, as you fall deeper, do the forces become unsurvivable. Time dilation compounds this. General relativity predicts that time passes more slowly in stronger gravitational fields. This is not a theoretical abstraction. It is a measured, confirmed phenomenon. GPS satellites have to account for the fact that their clocks run at different rates than clocks on the ground due to gravitational and velocity differences. Near a black hole, this effect scales up dramatically. A clock hovering close to the event horizon would tick extraordinarily slowly compared to a clock far away. To a distant observer watching someone fall into a black hole, the falling person would appear to slow down, their image redshifting and dimming as photons from them struggled to climb out of the deepening gravity well. The falling person would appear to asymptotically freeze at the horizon, never quite reaching it from the outside observer's perspective. From the perspective of the person falling in, no such freezing occurs. They cross the horizon in finite time, but the universe they see has changed. Looking outward, light from the entire future history of the universe would appear to blue shift and compress into a narrowing window above them. The deeper they fall, the more time outside accelerates from their perspective. For a supermassive black hole, this process takes long enough that the falling observer might have time to contemplate it. The light reaching their eyes from outside is increasingly ancient, increasingly blue-shifted, increasingly compressed into the small patch of sky still visible ahead. Everything behind them is the interior of a black hole. Everything ahead of them is the universe running forward at an impossible rate, visible through a shrinking aperture. None of this is solvable by technology. There is no engine, no material, no information we could encode into a spacecraft that would change the geometry inside the event horizon. The laws of physics as currently understood do not permit any path from inside to outside. Proposals exist. Rotating black holes theoretically contain mathematical features called ring singularities and hypothetical inner horizons with different properties. But whether any of these represent physical reality rather than mathematical artifacts is unknown. What is known is that nothing we have observed has ever escaped from inside an event horizon. Not light, not information, not anything. The geometry of a black hole is a one-way street. The road only gets stranger after the point where turning around stops being an option. Somewhere in the observable universe, a gamma-ray burst goes off roughly once per day. That number sounds almost routine until you understand what a gamma-ray burst actually is. In a matter of seconds, sometimes less, a single event releases more energy than our sun will produce across its entire 10 billion year lifetime. Not more energy than the sun produces in a year. Not in a million years. In its entire existence from ignition to death. All of that compressed into a flash that can last anywhere from a fraction of a second to a few minutes. These are not explosions in any sense that scales to human experience. They are the universe doing something for which there is no adequate analogy. There are two distinct types, and both are catastrophic in origin. Long gamma-ray bursts, which last more than 2 seconds and can stretch on for hundreds, come from the deaths of massive stars. When a star roughly 10 or more times the mass of our Sun exhausts its nuclear fuel, the core collapses. The outer layers fall inward at a fraction of the speed of light, rebound, and blow outward as a supernova. But in certain stars, the collapse doesn't stop at a neutron star. It continues all the way to a black hole. The infalling material forms a rapidly spinning disk around the newborn black hole, and in the process, two focused jets of energy and radiation fire outward from the poles at nearly the speed of light. Those jets are the gamma-ray burst. From the outside, the event briefly outshines the entire galaxy the star lived in. Hundreds of billions of stars, and this one dying object drowns all of them out. Short gamma-ray bursts follow a different path to the same catastrophic outcome. These events, lasting under 2 seconds, happen when two compact objects collide. Two neutron stars spiraling toward each other over millions of years, losing orbital energy to gravitational waves, finally merge, or a neutron star falls into a black hole. The collision releases an almost incomprehensible pulse of energy. In 2017, astronomers detected both the gravitational waves and the gamma-ray burst from exactly this kind of merger. A neutron-star collision 130 million light-years away. The burst lasted roughly 2 seconds. The gravitational wave signal had been building for 100 million years. The energy scales involved break ordinary thinking. A typical long gamma-ray burst emits something on the order of 10 to the power of 44 joules. The Sun's total lifetime energy output is roughly 10 to the 41 joules, so a single burst outpaces the Sun by a factor of 1,000 or more. Some of the most powerful events ever recorded release even more than that. The burst GRB 080916c, detected in 2008, occurred about 12 billion light-years away and released an estimated 9,000 times the energy of a typical supernova. Astronomers calculated that in the first few seconds, the event was brighter than 10 quadrillion suns. Those numbers stop meaning anything at a certain point. That may be the point. Most gamma-ray bursts are detected in galaxies billions of light-years away. The detectors that catch them, satellites like the Fermi Gamma-Ray Space Telescope and the Neil Gehrels Swift Observatory, register a sudden, brief spike of high-energy radiation arriving from some fixed point in the sky. Within hours, telescopes worldwide pivot to the location to catch the fading afterglow. The source galaxy, when identified, is almost always impossibly distant, and that distance is the only reason the observation is a scientific curiosity, rather than the last thing those instruments ever recorded. What would happen if one of these events occurred close by? Close, in this context, means within a few thousand light-years, still inside our own galaxy. The gamma rays would reach Earth at the speed of light, with no forewarning of any kind. There would be no magnetic field defense. Our magnetosphere, which handles the radiation environment described earlier in this series, is not remotely equipped to handle a directed gamma ray burst. The photons would slam into the upper atmosphere at energies that strip nitrogen and oxygen molecules apart, driving chemical reactions that destroy ozone. Not partially. The ozone layer, globally, would be gone in seconds. What follows is a surface exposed to full ultraviolet radiation from the sun, with nothing filtering it. UV levels would spike to hundreds of times their normal intensity. Photosynthesis collapses almost immediately. Marine phytoplankton, the base of ocean food chains, dies in the upper water layers. Animals exposed to direct sunlight suffer radiation burns and cellular damage. The cascade runs down every food web on the planet simultaneously. Recovery timescales, if any recovery happened at all, would be measured in millions of years. This is where the Ordovician mass extinction becomes relevant. 450 million years ago, roughly 85% of all marine species were wiped out in what remains one of the 5 largest extinction events in Earth's history. The pattern of that extinction is unusual. It appears sudden. It disproportionately affected shallow marine organisms, exactly the life forms most vulnerable to a UV spike following ozone depletion. Some researchers have proposed that a nearby gamma ray burst, directed at Earth, could account for the pattern. The geological record does not contain a direct GRB signature. There is no smoking crater, no iridium layer of the kind associated with the asteroid impact at the end of the Cretaceous. But the physics fits. A burst from within a few thousand light years, aimed in our direction, would leave no physical artifact in the rock, only dead things. Whether a GRB actually caused the Ordovician extinction is unknown and may never be resolved. But the proposal is scientifically serious enough that it gets published in peer-reviewed journals and cited by researchers studying both extinction events and cosmic hazard assessment. It sits in a peculiar category, an event with no confirmed occurrence but entirely plausible physics, no way to verify, and extinction-level consequences if true. The thing about gamma-ray bursts that separates them from almost every other danger in this series is the complete absence of warning. A rogue star, a black hole, a magnetar, all of these pose threats that, in principle, could be detected in advance given sufficient observational technology. Their positions can be mapped, their movements can be tracked. A gamma-ray burst cannot be predicted. There is no precursor signal. There is no astronomical configuration you can monitor to know one is coming. The burst travels at the speed of light, which means the radiation arrives at the same moment any electromagnetic warning would. The first indication that a GRB is pointed at Earth is also, unavoidably, the last. Some estimates suggest that any point in the galaxy has a non-trivial probability of being caught in the cone of a gamma-ray burst over timescales of hundreds of millions to billions of years. The Milky Way produces perhaps 1 or 2 gamma-ray bursts every few million years. Whether any of them point at Earth depends entirely on geometry. The burst cone is narrow, typically a few degrees wide, which reduces the probability significantly. But over geological time, the numbers are not reassuring. Life on Earth has survived for roughly 3.5 billion years. Over that span, the odds that none of the galaxy's gamma-ray bursts were aimed in this direction approach 0. Which means either we were lucky, or one or more of them may have already hit us, and we are reading the aftermath in the extinction record. There is currently no known gamma-ray burst primed to fire in Earth's direction. The star WR104, a massive Wolf-Rayet star roughly 8,000 light-years away, was identified years ago as a potential candidate, a star massive enough and close enough to pose a theoretical threat if it collapsed with the right geometry. Later analysis suggested the rotation axis is probably not pointed at us. Probably. The uncertainty is real and acknowledged. No one can say with certainty what angle a dying star's jet will take until after it fires. One detected event from 2004 put all of this in sharper focus. Magnetar SGR 1806-20, discussed in the previous section, produced a burst that briefly overwhelmed satellite detectors and measurably disturbed Earth's ionosphere. That object was 50,000 light-years away, on the far side of the galaxy. Researchers calculated that if the same event had occurred within 10 light-years of Earth, it would have been catastrophic. Magnetar flares are not gamma-ray bursts in the traditional sense, but they illustrate the same principle. Energy events at these scales affect the environment at distances that dwarf anything else in physics. The observable universe produces roughly one gamma-ray burst per day. On average, across all visible galaxies, something somewhere fires a beam of radiation energetic enough to sterilize planets, destroy atmospheres, and outshine entire collections of hundreds of billions of stars. Every day. The only reason that fact is historical trivia rather than an ongoing emergency is that almost all of them happen in galaxies so far away that the energy disperses before it gets here. The supermassive black hole at the center of the Milky Way, Sagittarius HA, has a mass of 4 million suns, and it occasionally does something extreme to the stars that get too close. The mechanism works like this. Stars near the galactic center don't travel alone. Many of them exist in binary pairs, two stars orbiting each other as they move through space. When one of these pairs drifts too close to Sagittarius A, the black hole's gravity doesn't treat both stars equally. It pulls harder on whichever star is closer. The pair gets disrupted. One star falls into a tight orbit around the black hole, captured. The other gets flung outward. The energy released by that capture gets transferred almost entirely to the ejected star, launching it away from the galactic center at speeds that can exceed 1,000,000 miles per hour. That is fast enough to escape the gravitational pull of the entire Milky Way. A star born somewhere near the galactic core, moving at those speeds, will eventually leave the galaxy entirely and travel through intergalactic space with nothing to stop it. Astronomers began finding these objects in the early 2000s. The first confirmed hypervelocity star was discovered in 2005. More followed. By now, researchers have identified hundreds of candidates scattered across the outer regions of the Milky Way, stars sitting in positions that make no sense under normal galactic dynamics. A star doesn't drift to the far outskirts of the galaxy through ordinary orbital mechanics in the time available. The only explanation that fits is that something threw them there with enormous force. Tracing their trajectories backward, the paths converge on the galactic center. The math points directly at Sagittarius A. What this means is that our galaxy is continuously ejecting stars. Not occasionally, not as a rare anomaly, but as a regular byproduct of the dense, chaotic environment near its central black hole. These objects are moving through the same galactic space that everything else occupies. They don't announce themselves. A hypervelocity star crossing the outer galaxy looks, at first, like any other star. Its speed only becomes apparent when you measure its motion carefully against the background. Without that measurement, it's invisible as a threat. The sheer velocity of these objects compounds the hazard they represent. A hypervelocity star moving at 1,000 kilometers per second carries kinetic energy proportional to its mass, multiplied by that speed squared. When gravitational forces are involved, that energy translates into severe perturbations across extraordinary distances. Unlike a slow-moving object whose effects diminish gradually with separation, a hypersonic encounter transfers tremendous force over a brief window of interaction. The faster an object moves, the harder it pulls as it passes. From any given vantage point in the galaxy, a hypervelocity star might approach and recede too quickly for meaningful detection or avoidance. The threat emerges from the darkness and vanishes again, having altered trajectories and trajectories of trajectories along its path. Now consider what happens when one of these objects passes through an inhabited region of the galaxy. Not a direct collision, which is extraordinarily unlikely given the vast distances between any two stars. The danger is subtler. A star passing within a few light years of a planetary system would exert gravitational influence on everything around it. Planetary orbits, which depend on a delicate and long-established balance of forces, could be nudged. A nudge of the right size and direction doesn't immediately destroy a planet. It shifts the orbit slightly, changes the eccentricity, alters the relationship between a planet and its star over time. Over thousands of years, that perturbation compounds. A planet that was once in a stable, habitable zone drifts inward or outward. The seasons change, the climate changes. Life, if it exists there, faces conditions it wasn't shaped by. The more immediate threat is the Oort cloud. Every star, like our Sun, is surrounded by a vast, diffuse shell of icy bodies at enormous distances, the frozen remnants of the original solar system. These objects are barely bound gravitationally. A passing star, even a distant one, tugs on them. Some get nudged onto new trajectories that send them falling inward toward the inner solar system. A single gravitational disruption of an Oort cloud could send thousands of comets on new paths over the following million years, increasing the frequency of impacts on any planets orbiting the interior. This is not theoretical. The solar system has experienced comet showers before. The geological record contains their signatures. The question of what triggered specific impact events in Earth's past is still open. A passing star is among the candidate answers, but hypervelocity stars are only one part of the problem. They're at least luminous. You can detect them if you're looking carefully enough. The interstellar medium between stars also contains something far harder to find. When solar systems form, the process is not clean. Planets assemble from the disk of material surrounding a young star through a long series of gravitational interactions. Not every object that forms ends up in a stable orbit. Some get ejected. Gravitational encounters between forming planets can throw objects outward with enough velocity to leave the system entirely. These are rogue planets, and they drift through interstellar space with no star, no light source, no warmth. They are cold, dark, and effectively invisible against the backdrop of space. They emit no light of their own. The only way to detect most of them is through gravitational microlensing, the brief brightening of a background star as the rogue planet passes in front of it. This requires precise alignment, careful monitoring of millions of stars, and a degree of luck in timing. Events like this last hours to days. Miss the window, and you've missed the planet. The numbers here are genuinely unsettling. Some estimates suggest rogue planets may outnumber the stars in the Milky Way. The galaxy contains roughly 200 to 400 billion stars. If rogue planets are even comparably numerous, the interstellar medium is filled with dark, invisible objects of planetary mass moving on trajectories that no survey has mapped. A spacecraft traveling between stars would have no reliable way to detect them in advance. At interstellar distances, the instruments available today would not see one until it was close enough that course correction might no longer be practical. There's a reason astronomers describe the space between stars as mostly empty. On average, it is. The distances are so large and the objects so sparse that direct collisions between any two things are vanishingly unlikely. But mostly empty is not the same as safe. It is not the same as known. The interstellar medium is a statistical environment. Individual paths through it are not surveyed. Individual objects in it are largely uncatalogued. And the deeper you travel into it, the more that matters, because the time available to respond to anything you encounter scales with how far you are from anywhere else. Hypervelocity stars and rogue planets represent two different flavors of the same problem. One is visible but moving at a speed that puts enormous energy behind any gravitational interaction. The other is invisible entirely, its presence unknown unless it happens to cross the right line of sight at the right moment. Both exist in the same interstellar space that any mission beyond the solar system would have to cross. Neither of them cares about trajectories or timetables or survival margins. They move through the galaxy according to physics, not convenience. The galaxy contains a significant population of dark, cold, invisible objects with no star and no light, and we have no reliable way to know where any of them are. Pull back far enough from any single star or galaxy and the universe resolves into something unexpected, a web, not a random scatter of points, not a uniform fog, a structure. Galaxy clusters connected by enormous filaments of gas and dark matter, filaments stretching hundreds of millions of light years from node to node, with vast empty regions between them where almost nothing exists. Astronomers call this the cosmic web, and it is the largest known structure in the universe. It is also one of the most disorienting things to contemplate, because the scale at which it becomes visible makes every object described in every previous section of this journey, neutron stars, magnetars, black holes, hypervelocity stars, shrink to something smaller than a dust grain on a map of a continent. The cosmic web formed because matter in the early universe was not distributed perfectly evenly. There were slight overdensities, regions where matter was fractionally more concentrated than average. Gravity amplified those differences over billions of years. Matter flowed toward the denser regions, draining away from the emptier ones. The overdense regions became filaments and walls. The underdense regions became voids. After 13.8 billion years of this process, the result is a structure that resembles, in photographs, the neural network of a brain, or the tangled threads of a vast three-dimensional net. The resemblance is not a metaphor that astronomers invented. It is what the data shows. The Milky Way sits inside this structure, not at a dramatic location, not at a major intersection of filaments, not deep inside a void. We occupy a relatively ordinary position within a modest cluster of galaxies called the local group, which itself sits near the edge of a larger supercluster called Laniakea. Laniakea was only mapped in detail in 2014. It contains roughly 100,000 galaxies and spans about 520 million light years. The fact that we did not know we lived inside it until 11 years ago says something important about how difficult it is to map structure at these scales from inside the structure itself. What Laniakea also revealed is that our entire local neighborhood is moving. Not just the ordinary motion of the Milky Way through space, but a bulk flow, a drift shared by hundreds of thousands of galaxies across an enormous region, all of them sliding in the same direction at roughly 2 million kilometers per hour. This was detected in the 1980s when astronomers noticed that distant galaxies were not receding from us at exactly the rates that the expansion of the universe would predict. Something was pulling. Something massive was introducing a systematic deviation from the expected pattern. The region toward which all of this motion converges became known as the Great Attractor. The Great Attractor is not a single object. It is a gravitational anomaly centered roughly 250 million light-years away, in the direction of the Norma constellation. The mass responsible for the pull is equivalent to tens of thousands of galaxies. For decades, studying it directly was nearly impossible because it sits almost exactly in the plane of the Milky Way, meaning that our own galaxy's gas and dust block most of the light coming from that direction. Astronomers had to work around the problem using X-ray and radio observations that could penetrate the obscuring dust. What they found was a region of extreme density, clusters of galaxies packed more tightly together than average, part of a larger gravitational basin that the entire local universe is draining into. We have been moving toward it for billions of years. We will continue moving toward it for billions more. There is something genuinely unsettling about this. Every star in the Milky Way, every planet, every object catalogued in every previous section of this journey is being carried towards something that humans did not even know existed 40 years ago. The motion is not violent, it is slow by cosmic standards, but it is continuous and it is unavoidable, driven by the gravitational architecture of the web we are embedded in. Now consider what lies between the filaments, the voids. If the filaments and clusters are where matter concentrated, voids are where it drained away from. They are regions that have been emptying for billions of years, growing larger as their edges lose material to the surrounding structure. Some of the largest known voids span 300 to 400 million light-years across. The Boötes void, discovered in 1981, contains almost no galaxies across a region roughly 330 million light-years in diameter. When astronomers first mapped it, the emptiness was so extreme that one researcher reportedly joked that if the Milky Way had been located inside it, humans would not have discovered other galaxies until the 1960s. Imagine existing in one. A civilization inside a cosmic void would face a sky unlike anything visible from Earth. No nearby galaxies. No large star clusters outside their own. In every direction, darkness, interrupted at the very limit of detection by the faint, smeared light of distant galaxy walls billions of light-years away. Their observable universe would look nearly empty because, for all practical purposes, it would be. The raw material for stars, for planets, for chemistry, for any of the processes that made something like this possible would be sparse to the point of irrelevance. Such a civilization, if it existed, would have every reason to conclude the universe contained almost nothing, because from where they were standing, it almost did. Voids are not static, they are growing. As matter continues to drain toward the filaments and clusters, the voids get larger and emptier. dark energy accelerates this process, pushing the edges of voids outward, widening the gaps between the filaments. The cosmic web is not a fixed architecture, it is evolving, and the direction of that evolution is toward greater contrast, denser filaments, emptier voids, a structure becoming more pronounced even as the objects within it drift farther apart. What dark energy does to the cosmic web on long timescales is one of the more philosophically difficult things to sit with. Right now, thousands of galaxies are visible to us in principle. With a sufficiently powerful telescope, we could observe them, but the expansion of the universe is not uniform across all scales. On the largest scales, space itself is stretching. Distant galaxies are receding from us, not because they are moving through space in the ordinary sense, but because the space between us and them is growing. For galaxies beyond a certain distance, called the Hubble radius, this recession is already faster than light. We can still see them because the light they emitted in the past, when they were closer, is still traveling toward us. But any light they emit now will never reach us. It is already being carried away faster than it can travel inward. This means there is a cosmological horizon, a boundary beyond which events are permanently invisible to us. And that horizon is shrinking. As dark energy continues to accelerate the expansion, galaxies that are currently just within our observable range will eventually cross that boundary and disappear, not because they are destroyed, because the space between us and them will be growing faster than light can cross it. They will vanish from the universe we can observe in principle, not just the universe we happen to be able to see with current instruments. Estimates vary, but in roughly 1 to 2 trillion years, the only galaxies gravitationally bound to us, the ones close enough that local gravity holds them against the expansion, will be all that remains visible. Everything else will have receded beyond the horizon. A civilization that arose in the Milky Way at that point would look out and see a small island of perhaps a few dozen galaxies surrounded by complete darkness. They would have no observational evidence that the cosmic web had ever existed. No filaments, no superclusters, no Booty's void stretching hundreds of millions of light years. No great attractor pulling millions of galaxies across an enormous basin of space. All of it gone beyond the reach of light. The cosmic web is the largest structure humanity has ever mapped, and the universe is methodically erasing it from the category of things that can ever be known. Dark energy means the part of the universe we can observe in principle is getting smaller every year, and the process will not stop. The universe contains somewhere around 2 trillion galaxies, each containing on average a few 100 billion stars, most of which probably have planets. Run those numbers and the implied count of potentially habitable worlds becomes so large it stops feeling like a number. It becomes a statement. Life should be everywhere. Intelligence should be everywhere. The universe has had 13.8 billion years to work with, and the raw material, carbon, water, energy gradients, is not rare. It is among the most common chemistry in the cosmos. So the question that follows is not a small one. Where is everybody? This is the Fermi Paradox, named for physicist Enrico Fermi, who supposedly asked exactly that question over lunch in 1950. The logic is straightforward enough to state in 2 sentences. The galaxy is old enough and large enough that any civilization with even modest spacefaring capability could have colonized it entirely within a few tens of millions of years, a small fraction of its total age. And yet every telescope we have ever pointed at the sky has returned the same answer. Silence. Not a weak signal, not an ambiguous artifact, nothing that holds up. The galaxy has had billions of years to fill with voices, and from where we stand, it is completely quiet. The Milky Way alone is roughly 13 billion years old. Stars capable of hosting rocky planets at the right temperatures formed throughout most of that history. If even a handful of civilizations appeared in the first few billion years and expanded at 1% of the speed of light, a crawl by any ambitious standard, they would have reached every corner of this galaxy long before Earth had its first complex cell. There should be evidence, signals, structures, something detectable by instruments far less sophisticated than the ones we have now. There is not. That absence is the paradox, and it has no comfortable resolution. The first explanation is the one people reach for instinctively, because it is the least disturbing. Maybe life is just genuinely, extraordinarily rare. Not rare in the sense of uncommon, rare in the sense of almost impossible. The conditions that produced Earth were not simply favorable. They may have been a combination of factors so specific that replicating them anywhere else in the observable universe is vanishingly unlikely. The right size star, at the right stage of evolution, with a large gas giant in the outer system deflecting incoming debris, a stabilizing moon of just the right mass, a magnetic field, plate tectonics, a near-perfect orbital distance. Change any one of these significantly, and the outcome changes. This is called the rare Earth hypothesis, and if it is correct, then the silence makes sense. There is no one out there. We are not the product of common processes. We are an accident so unlikely that it may have happened only once. That explanation is unsettling in a particular way. It replaces a universe full of life with a universe that is mostly dead by default, and it places us at the center of something that was never intended to produce us. But there is a darker answer, one that most researchers consider more seriously, and one that the previous sections of this journey have been quietly building toward: the Great Filter. The idea is this: somewhere between simple chemistry and a civilization capable of leaving its home star, there is a step, or several steps, that almost nothing survives. A barrier so difficult to clear that the universe's track record of producing spacefaring intelligence is effectively zero. The question that makes this terrifying is not whether the filter exists. The question is where it sits relative to us. If the filter is behind us, if we have already cleared the hard step, the unlikely emergence of complex cells or multicellular life or intelligence itself, then we are among the rare lucky ones, and the future may still be open. If the filter is ahead of us, we have not hit it yet. Something out there kills every civilization before it gets far enough to leave a permanent mark on the galaxy, and we are currently approaching whatever that thing is. Researchers have proposed candidates: nuclear weapons proliferating before institutions are stable enough to manage them, climate systems destabilized faster than a civilization can adapt, a biological agent, natural or engineered, efficient enough to end complex society before spacefaring becomes self-sustaining. The list goes on. Every item on it is something we have already invented or are already doing. None of them require outside intervention. The filter, in many versions of this hypothesis, is not something the universe does to civilizations. It is something civilizations do to themselves. But there is a version that connects directly to everything described in the sections that came before this one. What if the filter is not internal at all? What if the universe itself is simply too violent an environment for complex life to persist long enough to spread? Consider the timeline. A civilization needs millions of years to develop, from biology to radio signals to genuine spacefaring. During that window, it sits on one planet, in one solar system, entirely exposed to everything the galaxy can produce. A magnetar in the right orientation fires a burst at the wrong moment. A gamma ray burst from a dying massive star in a neighboring spiral arm sweeps across the inner galaxy. A hypervelocity star disrupts the Oort cloud and sends a cascade of comets inward on decade-long collision courses. None of these require the civilizations to do anything wrong. They just require bad luck in a galaxy that produces violent events on a continuous basis. The cosmic hostility described throughout this journey is not background noise. It is an active and ongoing threat to everything alive, everywhere, always. The radio silence points in the same direction. Astronomers have been scanning the sky for deliberate signals for more than 6 decades now. The instruments have improved dramatically in that time. The sky coverage has widened. The frequency ranges have expanded. Nothing has come back that holds up to rigorous analysis. There was one candidate, the famous WOW signal detected in 1977, a narrowband radio pulse that briefly matched the profile of what a deliberate transmission might look like. It was never repeated. It was never explained. It remains the most intriguing data point in 6 decades of searching, and it is a single event from almost 50 years ago that could not be confirmed. One explanation for the silence that does not require catastrophe is subtler and in some ways stranger. Maybe civilizations do not use radio. Maybe radio is a brief phase, a few centuries at most, between no technology and something far beyond our current conception. A civilization 1,000,000 years more advanced than us might communicate through methods we have not discovered, at frequencies or via physical phenomena we do not yet know to look for. We might be surrounded by chatter we cannot decode because we are still listening for something that advanced civilizations stopped doing long ago. This explanation at least keeps the galaxy populated, but it also places us in a position of profound ignorance, scanning with the wrong instruments, at the wrong frequencies, searching for a kind of signal that has long since been abandoned everywhere else. Some researchers have suggested the silence implies something stranger still. The simulation hypothesis occupies this territory. The idea that what we call the universe is itself a computational construct, and that the silence is simply an unexplained artifact of its architecture. This is not a scientific hypothesis in any testable sense, but it gets raised repeatedly in discussions of the Fermi Paradox, because conventional explanations keep running into the same problem. The numbers do not work. The galaxy should be full by now. It is not. What makes the paradox land hardest, after spending time with the objects and forces described in this video, is this. The universe is not indifferent to life in the way a blank field is indifferent. It is specifically, mechanically hostile. Magnetars erupt, black holes shred, gamma ray bursts sweep across hundreds of light years in seconds. Rogue stars disrupt solar systems. Space itself is filled with radiation that dismantles biology at the molecular level. The environment is actively working against the persistence of anything fragile enough to think about it. And the persistence required to go from one planet to 2 is enormous, thousands of years of uninterrupted civilization in an environment where the timeline for potential catastrophe is measured in the same units. The silence may be the universe's most honest data point, not a puzzle to be solved, an answer. The silence itself is one of the most unsettling things about deep space, because the longer it holds, the more it suggests that whatever is out there waiting, we have not encountered it yet. Dark energy is the dominant component of the universe, making up roughly 68% of its total energy content, and right now it is pushing space apart at an accelerating rate. That sentence is worth sitting with for a moment. The majority of the universe is not matter, not stars, not gas clouds, not black holes. It is something we cannot see, cannot sample, cannot detect directly, and do not understand. We know it exists because of what it does. And what it does, right now, is win. Against gravity, against structure, against everything that has spent the last 13.8 billion years trying to hold itself together. The reason you don't feel this happening is that dark energy operates on enormous scales. Inside a galaxy, inside a solar system, inside a room, gravity is easily strong enough to hold things in place. The expansion of space on those scales is negligible. A hydrogen atom has no idea the universe is expanding. Neither does the Earth or the Sun or the Milky Way. The gravitational bonds on those scales are too strong. The expansion loses, locally, everywhere you can look directly. But zoom out far enough and dark energy is already winning. Distant galaxy clusters are receding from us faster and faster. Regions of the universe that were once reachable in principle are now moving away faster than light, disappearing behind a cosmological horizon we cannot cross. This is already happening. It is not a future scenario. It is the present reality. The question is whether it stays this way or gets worse. Here is where the scenario called phantom dark energy enters the picture. The standard cosmological model treats dark energy as a constant, a fixed background pressure woven into the fabric of space-time itself. Under that assumption, the expansion accelerates, but it accelerates at a steady rate. Galaxies recede, the voids between filaments grow, the observable universe slowly shrinks as distant regions cross the horizon. But local structure, the clusters and galaxies and solar systems that gravity holds together, survives indefinitely. That is the relatively comfortable version. Phantom dark energy is different. In this scenario, the energy density of dark energy does not stay constant over time. It grows. The pressure it exerts on space-time becomes increasingly negative, accelerating the expansion not at a steady rate, but at an accelerating rate, compounding on itself, the expansion feeding the expansion. Under this model, the force driving space apart eventually grows strong enough to overcome gravity, not just on cosmological scales, but on smaller and smaller ones. And then it does not stop. The cascade that follows has a name, the Big Rip. It proceeds in stages, each stage shorter than the last, each one dismantling something that seemed permanent. The first structures to go are the largest ones. Galaxy clusters, the gravitational superstructures that contain hundreds or thousands of galaxies bound together, begin to dissolve. The expansion of space, now growing strong enough to compete with their collective gravity, pulls them apart. Galaxies that have orbited each other for billions of years drift outward, separating into isolation. This phase, in current theoretical models, begins perhaps 1 billion years before the final singularity. Then the individual galaxies go. The stars that make up a galaxy are held in their orbits by the combined gravity of all the mass inside it, including its dark matter halo. When the expansion grows strong enough to overcome that, the galaxy shreds. Stars scatter outward. The disk dissolves. What was once a coherent structure containing hundreds of billions of stars becomes a dispersing cloud, and then nothing recognizable at all. This happens roughly 60 million years before the end. Solar systems fail next. The gravitational bond between a star and its planets is much stronger than the tenuous gravity holding a galaxy together, but phantom dark energy does not stop. Expansion continues to accelerate. Planets spiral outward from their stars, orbits destabilizing and widening until they are no longer orbits at all. 3 months before the final singularity, the planets are gone. The Sun, if our Sun survived that long, would find itself alone. Minutes before the end, stars themselves come apart. The expansion of space grows strong enough to overcome the self-gravity that holds a star's mass together. The outer layers no longer have anything anchoring them. The star expands uncontrollably, unable to maintain the internal pressure gradients that define it as a star. It does not explode. It simply spreads apart, its matter dispersing into the expanding void. Then the smaller scales. Roughly 16 minutes before the final singularity, planets, moons, any solid bodies that remain, are pulled apart as the expansion overcomes the gravitational self-cohesion of rocky objects. The rubble fields spread and dissolve, and then chemistry fails. Molecules depend on electromagnetic bonds between atoms, electron clouds overlapping and sharing energy in configurations that give matter structure and properties. When the expansion of space itself exceeds the scale at which those bonds can operate, the molecules break. Not because they were heated or struck or chemically altered, because the space between atoms is growing faster than the bonds can accommodate. Water, rock, iron, the organic molecules that make up living things, all of it simply comes apart. This happens in the final seconds. Last of all, atoms themselves. The nucleus of an atom is held together by the strong nuclear force, the most powerful force in physics, binding protons and neutrons at distances of roughly 10 to the negative 15 meters. The Big Rip does not care. When the expansion rate diverges to infinity, it overwhelms even this. Protons and neutrons separate. The nucleus ceases to exist. Matter itself, at its most fundamental level, is dissolved not by heat or pressure or any physical process we have ever observed, but by the geometry of space-time expanding without limit. The final singularity is not a singularity of matter compressing, the way a black hole's interior is. It is a singularity of expansion. The scale factor of the universe, the mathematical quantity describing how stretched space is, diverges to infinity in a finite amount of time. At that moment, the mathematics of general relativity break down entirely. Whatever happens in those final instants, we do not have a theory that can describe it. Current estimates place this, if phantom dark energy is the correct model, approximately 22 billion years from now. That is nearly twice the current age of the universe. It is not imminent by any ordinary measure, but the physics that would drive it are already present. Dark energy is already accelerating the expansion. We do not know yet whether its density is constant or growing. The measurements are difficult, the uncertainties large. The equation of state parameter that would distinguish phantom dark energy from a cosmological constant sits inside a range that current observations cannot fully exclude in either direction. What makes the Big Rip unsettling is not the timescale, it is the mechanism. Every other catastrophic scenario in cosmology involves matter doing something violent to other matter. Stars exploding, black holes consuming, gamma-ray bursts firing through galaxies. All of it is matter, energy, force acting on force. The Big Rip is different. It is space-time itself that kills everything. Not a weapon aimed at the universe's own geometry, turning against its contents. The expansion that carried galaxies apart in the early cosmos, the same expansion that gave structures room to form, becoming, at the end, the thing that unravels every structure that ever existed. There is no warning. There is no possibility of escape or resistance. There is no place in the universe to hide from the expansion of space, because space is what everything is embedded in. The last atoms do not go violently. They go because the distance between their constituents has become infinite. The Big Rip is not the most likely ending for the universe, but it is the most violent one, and the physics that permit it are already operating in the background of everything. In the early universe, before stars had been burning for more than a few billion years, the centers of galaxies were far more violent places than they are today. The objects responsible for that violence have a name that does not do them justice: quasars. The word sounds almost mundane. What it describes is not. A quasar is what happens when a supermassive black hole at the center of a galaxy begins consuming material at an extreme rate. Gas, dust, and shredded stellar matter fall inward, forming an accretion disk that heats to hundreds of millions of degrees through friction and compression. That disk glows. It does not glow the way a star glows. It glows the way nothing else in the observable universe glows. A single quasar can outshine an entire galaxy of hundreds of billions of stars. Some outshine their host galaxies by a factor of hundreds. The most luminous ever detected outshine theirs by a factor of thousands. The energy involved defies intuition. Astronomers measure luminosity in units calibrated to the sun, and even those numbers stop feeling like numbers at quasar scales. The most powerful quasars emit energy equivalent to trillions of suns burning simultaneously, all from a region of space smaller than our solar system. The accretion disk itself is the engine. As material spirals inward toward the event horizon, gravitational energy converts to radiation with remarkable efficiency. More efficient, in fact, than nuclear fusion. Stars convert about 0.7% of their mass to energy through fusion. A well-fed quasar accretion disk can convert closer to 40% of infalling mass directly into radiation before it crosses the horizon. That efficiency is part of why the output is so staggering. Then there are the jets. Some quasars don't just radiate outward in all directions. They focus a portion of their energy into narrow beams of plasma fired from the poles of the black hole at close to the speed of light. These relativistic jets extend outward into space for distances that are difficult to hold in the mind. Not thousands of light years, not millions. Some jets have been measured stretching for tens of millions of light years, longer than the distance between the Milky Way and many nearby galaxies. Whatever those jets encounter, they encounter it at relativistic speed and at temperatures that reduce any distinction between matter and plasma to a technicality. A quasar jet passing through a galaxy is not a gradual process. It is a disruption of everything in its path. Quasars were first detected in the 1960s, and for years astronomers argued about what they were. They appeared star-like in optical telescopes, compact points of light, but their spectra made no sense. The emission lines were shifted so dramatically toward the red end of the spectrum that the objects producing them had to be moving away from Earth at a significant fraction of the speed of light. That meant they were not nearby objects. They were at cosmological distances, billions of light years away. And if they were that far away and still that bright, the amount of energy they were producing was so far outside any known physics that the astronomical community spent years simply trying to accept the numbers. The answer, eventually, was supermassive black holes consuming matter faster than anything else in the known universe. What the distances tell us is also important, because light takes time to travel. Looking at distant quasars is looking into the past. The quasars observed at the greatest distances are being seen as they existed 10 to 12 billion years ago in the early universe, when galaxies were younger and denser and their central black holes had abundant material to consume. Quasars were common then. They are rare now. The universe has evolved. Galaxies have consumed the loose material in their cores, and most central black holes have quieted down. The quasar era is largely over. What we see when we look at those distant bright points is a record of conditions that no longer generally exist, a snapshot of a more violent time. That evolution matters because it raises a question closer to home. The Milky Way has a supermassive black hole at its center. Sagittarius A, roughly 26,000 light-years from Earth, contains about 4 million solar masses compressed into a volume smaller than our solar system. Right now, it is quiet. There is not enough material falling into it to power any significant emission. By the standards of active galactic nuclei, Sagittarius A is essentially dormant. It occasionally flares when a gas cloud or other material passes too close, but these events are brief and relatively dim. Nothing about the current Milky Way center resembles a quasar. But quiet is not the same as always quiet. Evidence has accumulated that Sagittarius A was not always this calm. The Fermi bubbles, two enormous lobes of high-energy gas extending above and below the galactic plane for roughly 25,000 light-years in each direction, are one piece of that evidence. They appear to be the remnant of some powerful energy release from the galactic center, most likely within the last few million years. The leading explanation is that Sagittarius A went through a period of significantly elevated activity, consuming infalling material at rates far beyond what it processes today, and the radiation and particle output of that period inflated those enormous structures into the galactic halo. They are still there, still expanding, a record written in hot gas of something that happened when our ancestors were not yet fully human. There are other signatures too. Certain gas clouds near the galactic center are illuminated in ways that suggest they are being lit by a radiation source far brighter than the current faint activity of Sagittarius A. The geometry of the illumination points back to the galactic core and suggests the source was active a few 100,000 years ago. Astronomers call this the Scrö-AJ light echo. The black hole flared, sent out a burst of ionizing radiation, and that radiation is still moving outward through the surrounding gas, lighting up clouds like a pulse of light sweeping across a fog bank. We are seeing the aftermath of an event that the black hole itself has long since moved past. What would happen if Sagittarius AJ became fully active again? Not a brief flare, but a sustained period of quasar-level accretion. The radiation environment in the inner Milky Way would change completely. High-energy X-rays and ultraviolet radiation streaming outward from the galactic center would begin stripping the atmospheres of any planets within range and disrupting the chemistry of any systems lying along the path of enhanced radiation. The inner galaxy, already a region of dense stellar populations and elevated radiation compared to our quiet outer suburb, would become genuinely hostile to biological complexity. How far that effect would reach depends on the intensity and duration of the active phase, but the inner few thousand light-years of the galaxy would be bathed in conditions nothing like what currently exists there. We live far enough from the galactic center, roughly halfway out toward the edge of the disk, that a moderate active phase in Sagittarius A might not be immediately catastrophic for Earth. But the margins are not infinite, and the history of our own galaxy suggests these events are not hypothetical. They happened before. The black hole at the center of the Milky Way is quiet right now, but the evidence that it has not always been quiet is written in the gas clouds and radiation fields that still surround it. The Milky Way galaxy may contain as many as 100 million stellar mass black holes, and almost none of them have ever been directly detected. This is not a gap in our instruments that a better telescope will eventually close. It is a fundamental property of what these objects are. A black hole with no companion star, no gas cloud falling into it, no accretion disk heating to millions of degrees. Such an object produces nothing. No light, no radio waves, no X-rays, nothing that any detector built by human beings can currently sense at any meaningful distance. It simply exists, moving through the galaxy on its orbital path, occupying space the way any massive object does, and announcing itself to absolutely no one. To understand how many of these objects the galaxy has accumulated, you have to think about timescales. The Milky Way is roughly 13 billion years old. Over that entire span, massive stars have been forming, burning through their fuel in millions of years rather than billions, and collapsing. Every star with a mass somewhere above 20 times that of our Sun is a candidate to leave a black hole behind when it dies. The galaxy has been manufacturing these objects for almost its entire history. 100 million is not an upper estimate. Some calculations push that figure higher. What it means, practically, is that if you were to pick a random point in the interstellar medium and ask whether a wandering black hole was somewhere in the general vicinity, the honest answer would be that we have no way to rule it out. For most of astronomical history, this was an accepted theoretical reality that could not be tested. You cannot point a telescope at nothing and confirm it is a black hole. The object emits no signal. There is no glow, no pulse, no characteristic radiation to distinguish it from the empty space around it. Astronomers knew these objects had to exist in enormous numbers, and they had essentially no way to find any individual one. The population was inferred from stellar evolution models and the known rate of massive star formation, not from observation. It was one of the strangest situations in modern astronomy, a category of object numbering in the hundreds of millions, scattered through the same galaxy we live in, and nearly invisible by definition. Then a technique offered a narrow window. Gravitational microlensing works because mass bends light. When a massive object passes in front of a more distant star from our line of sight, its gravity acts like a lens, bending and briefly magnifying the background star's light in a characteristic way. The brightening follows a specific curve as the lensing object moves across the line of sight and then moves away. If the lensing object is a star, that star can be seen directly, and its mass can be calculated from the brightening curve. If the lensing object is invisible, if nothing shows up in follow-up observations at any wavelength, then you have a candidate for a dark compact object, a neutron star, or a black hole. In 2022, astronomers confirmed the first direct detection of a solitary wandering black hole using exactly this method. The data came from years of monitoring by the Hubble Space Telescope and ground-based surveys watching hundreds of millions of stars in the direction of the galactic center, waiting for microlensing events. The event in question, catalogued as MOA 2011 BLG 191 and also designated OGLE 2011 BLG 0462, lasted for roughly 270 days, an unusually long duration that immediately suggested something more massive than a typical star was doing the lensing. Follow-up astrometric measurements, tracking the tiny shift in the apparent position of the background star as the lensing object moved past, allowed astronomers to pin down the mass. The result was somewhere between 6 and 10 solar masses. Nothing at that mass and that degree of darkness is going to be a neutron star. The conclusion was a black hole. Several solar masses, moving at a specific velocity through the galaxy, confirmed and isolated for the first time as a solitary wandering object. The thing worth sitting with is what that detection required. Years of continuous monitoring, hundreds of millions of background stars watched simultaneously, an event that lasted most of a year. Hubble observations precise enough to track positional shifts measured in micro-arc seconds, and the result was the detection of a single object out of a population that may number 100 million. The ratio between the effort and the yield suggests something about the scale of the problem. Finding one wandering black hole required essentially the maximum observational effort currently available to astronomy. The other 100 million are still out there, individually undetected, individually unlocated. What does this mean for anything moving through interstellar space? A spacecraft on a journey between stars would be traveling through the same galactic medium where these objects are distributed. The distances involved in interstellar travel are so vast that even with 100 million black holes distributed across the galaxy's disk, the average spacing between them is enormous. A direct encounter is not the likely concern. The concern is subtler than that. It is the question of what you can know in advance about what lies along your path. A rogue black hole has an escape velocity exceeding the speed of light at its event horizon, and it produces no emission of any kind at the distances relevant to navigation. The first indication that one was nearby would be gravitational, a slight, then increasing, then dramatic perturbation of the spacecraft's trajectory. At stellar mass scales, the tidal forces near a black hole become lethal well before the event horizon. For a spacecraft traveling at any speed achievable with foreseeable technology, the time between first detectable gravitational influence and meaningful tidal disruption could be short enough that course correction would require precision and reaction times far beyond anything currently possible. This is not the plot of a disaster scenario. It is the quiet arithmetic of traveling through a galaxy with a hidden population embedded in it. The interstellar medium is not a clean, empty corridor. It contains gas, dust, rogue planets, hypervelocity stars, and an unknown number of objects with the gravitational signature of collapsed stellar remnants and no corresponding light source. A civilization planning a multi-thousand-year journey between stars would be planning that journey through a medium that cannot be fully mapped in advance by any detection method currently available or theoretically obvious. The 2022 detection was a landmark. It confirmed that the population of wandering black holes is not purely theoretical. These objects can be found, one at a time, with extraordinary effort and the right alignment of geometry. But it also made clear how far that method is from a census. Microlensing requires a background source, a specific alignment, and continuous monitoring over the duration of the event. It finds the objects that happen to cross a monitored line of sight at the right moment. It cannot be used to survey the general galactic volume the way a telescope can survey stars. The 100 million is a population. The detections are a trickle. There is something specific about this class of object that sets it apart from the other dangers described so far in this journey outward. Magnetars announce themselves with bursts of gamma radiation powerful enough to disturb Earth's ionosphere from 50,000 light-years away. Gamma-ray bursts are detected across the observable universe. Even the quietest neutron stars can be located by their X-ray emissions or their slowing rotation. A wandering black hole gives you nothing. It is not a threat that scales with distance in a way that provides warning time. It does not broadcast its location. It waits in the dark, not with any intent, but with a patience that amounts to the same thing. The galaxy is full of invisible gravity wells moving silently through the same space everything else occupies, and the only way to find most of them is to wait for something to line up behind them. The nearest star to our Sun is Proxima Centauri, and at 4.2 light-years away, it is our closest neighbour in a way that makes neighbour feel like the wrong word. A light-year is roughly 5.9 trillion miles. Multiply that by 4.2. The number that comes out is not something a human brain was built to hold. Every probe, every spacecraft, every object humanity has ever launched into space would need approximately 70,000 years to cover that distance at its top speed. The fastest we have ever moved anything is around 40,000 miles per hour, achieved by the Parker Solar Probe during its closest approaches to the Sun. That sounds fast. It is not fast enough, not even close. This is the problem that sits underneath every other problem in deep space exploration, and it is unlike the radiation problem or the vacuum problem or the magnetar problem in one fundamental way. Those are engineering challenges, at least in principle. The scale problem is not. The speed of light is not a technological barrier waiting to be cleared by a sufficiently advanced civilization. It is a constraint written into the geometry of space-time itself. Nothing with mass can reach it. Nothing can exceed it. This is not a current limitation. It is a permanent one, built into the structure of the universe at the same level as gravity and electromagnetism. Understanding that changes how you read every other number in this video. At the speed of light, a speed no physical object can achieve but a useful theoretical benchmark, the trip to Proxima Centauri takes 4.2 years. That is the absolute minimum. That is the fastest anything could possibly travel that distance. And Proxima Centauri is our nearest neighbour. The next nearest stars after that are the Alpha Centauri system, at roughly the same distance, and then Barnard's star at 5.96 light-years. After that, the distances grow quickly. The nearest 100 stars to our Sun are spread across a volume roughly 25 light-years in radius. At light speed, crossing that volume takes 25 years. At the Parker Solar Probe's top speed, it takes over 400,000 years. The Milky Way is 100,000 light-years across. A radio signal sent from one edge of the galaxy to the other takes 100,000 years to arrive. The civilization that sent it has had 100,000 years to change, collapse, or disappear entirely before any reply could possibly return. Even within a single galaxy, communication across the full diameter is effectively impossible on biological timescales. You could send a message, and the species receiving it would be unrecognizable to you by the time any answer came back, assuming you still existed at all. The center of the Milky Way is roughly 26,000 light-years from Earth. If something catastrophic happened there right now, if Sagittarius A suddenly flared, if a magnetar detonated, if some event sent a wave of radiation outward at the speed of light, we would have no warning. The first indication would be the event itself arriving at our location 26,000 years from now. There is no telegraph system that outpaces light. The universe enforces a hard communication lag across every distance larger than what light can cover in a reasonable time, and reasonable time, at cosmic scales, runs out very quickly. Now scale up further. The observable universe, the sphere of space from which light has had time to reach Earth since the Big Bang, across 13.8 billion years, has a diameter of roughly 93 billion light-years. That number is larger than 13.8 billion times 2, because space itself expanded during the journey of that light, carrying the sources of the light farther away while the light was in transit. The observable universe contains an estimated 2 trillion galaxies. Each galaxy contains hundreds of billions of stars. The numbers become almost meaningless very quickly. Here is where it becomes genuinely unsettling. Most of what sits inside that 93 billion light-year sphere is not just unreachable today, it is permanently, physically unreachable by any object from any location near Earth under any circumstances, regardless of technology. The reason is dark energy. Space between distant objects is expanding, and in the far reaches of the observable universe, that expansion is happening faster than light could cross the growing distance. Galaxies beyond a certain threshold, the cosmological horizon, are receding from us faster than light travels. They are not moving through space faster than light. Space itself between us and them is expanding at that rate. The distinction matters physically, but the practical result is the same. Any signal or object we sent toward them today would never arrive. The expansion carries those galaxies permanently beyond reach. This means there are objects you can see right now with a telescope that you can never visit, never send a probe to, never communicate with in any meaningful exchange. You can observe them. You cannot reach them. The universe displays what it will not permit you to touch. What would it actually mean for a civilization to attempt serious exploration of even a modest portion of the galaxy? Consider a generation ship, a spacecraft large enough to sustain a self-contained population across multiple human generations, traveling at some fraction of the speed of light. The fastest plausible propulsion concepts currently discussed in serious physics literature might achieve somewhere between 1 and 10% of the speed of light under ideal conditions and enormous energy expenditure. At 1% of light speed, the trip to Proxima Centauri takes 420 years. 14 generations, approximately. The people who arrive would be the distant descendants of the people who left. At that speed, crossing the Milky Way would take 10 million years. Any meaningful survey of the galaxy's stellar population would require timescales longer than human civilization has existed by factors of thousands. And this still assumes you know where you are going. The rogue black holes discussed earlier are invisible. Rogue planets are invisible. Interstellar space is not empty. It contains objects with no light signatures moving on paths that cannot be fully catalogued in advance. A multi-thousand-year voyage through the interstellar medium is not a voyage through known territory. It is a journey through a space whose contents cannot be fully mapped, at speeds where course corrections take years to execute. The psychological weight of this deserves its own moment. Imagine a crew on a generation ship, 100 years into a 400-year voyage to the nearest star. Earth is so far away that a radio signal takes years to arrive. The civilization that launched the ship has changed in ways the crew cannot know in real time. The crew cannot turn back, not practically, not with the fuel available, not without another century of deceleration. They are committed to an endpoint none of them will live to see. What holds a community together under those conditions? What does identity mean when your home world is a historical artifact? These are not problems engineering can solve. Some physicists have explored theoretical frameworks that might permit faster than light travel, the Alcubierre warp drive being the most discussed. The concept involves compressing space-time in front of a vessel and expanding it behind, effectively moving the vessel without it, technically exceeding light speed within its local frame. The energy requirements calculated for even a modest version of this drive are on the order of the mass energy equivalent of Jupiter. No known energy source approaches this. The exotic matter required to stabilize the geometry may not exist. The concept remains a mathematical curiosity, not an engineering blueprint. Even if every other problem was solved, the scale remains. There is a version of this that is perhaps the most sobering thought in cosmology. As dark energy continues to accelerate the expansion of the universe, the number of galaxies observable from Earth will decrease over time. Galaxies now visible will eventually cross the cosmological horizon and vanish from our observable sphere permanently. The universe as we can see it is getting smaller, not larger. Civilizations in the far future will look out at a smaller cosmos than the one we observe today. They will have less to see and less, in principle, to reach. The universe is not hostile to life in a personal way. It is simply built on a scale that makes life's presence in it almost geometrically impossible to spread. The most likely ending for the universe is not an explosion or a catastrophic rip. It is something quieter and in its own way more final. Everything covered in this video so far, the magnetars, the gamma-ray bursts, the black holes, the rogue stars, those are violent things. They are loud, they announce themselves. What is coming at the end of cosmological time is the opposite of that. No flash. No catastrophic event that a hypothetical observer could point to and say, there, that was the moment. Just a slow, irreversible draining of everything that makes the universe structured, warm and alive. The process has a name. Physicists call it heat death, and it is the most probable fate of everything that exists. The second law of thermodynamics is one of the most ironclad statements in all of physics. Entropy, the measure of disorder in a system, always increases in a closed system. Always. There are no known exceptions. Small pockets of order can form locally, but only by exporting disorder somewhere else. Stars burn because a gravitational collapse concentrated matter into a tight, hot core, creating a steep energy gradient that fusion can exploit. Life exists because sunlight pours energy into the biosphere, and the biosphere offloads waste heat into the cold of space. Every ordered thing you can name exists because it is borrowing against a gradient that is slowly being exhausted. The universe as a whole is the closed system, and the universe is running down. Right now, the universe is roughly 13.8 billion years old. That sounds enormous. Against what is coming, it is almost nothing. The current era of cosmological history, the stelliferous era, the age of stars, will continue for an almost incomprehensible span of time. Not billions of years, trillions. The most common stars in the galaxy are not stars like the Sun. They are red dwarfs, small dim objects that burn so slowly and so efficiently that they can sustain fusion for timescales the human mind simply was not built to process. The least massive red dwarfs, stars containing perhaps a tenth of the Sun's mass, will keep burning for roughly 10 trillion years. That is 10 to the 13th power years. The universe is currently less than 14 billion years old. These stars will still be burning 1,000 times longer from now than the universe has currently existed. But they will go out, one by one, over those vast stretches of time. Every star in every galaxy will exhaust its hydrogen. The last ones will sputter and cool. The stelliferous era will end not with an event, but with a slow, galaxy-wide dimming, the last red dwarf fading from something dim to something dark. By the time the final star goes cold, the universe will be around 100 trillion years old, and the darkness that follows that moment will last far, far longer than the light did. What few observers might remain at such a distant time would witness something profound: the universe's transition from a place of stellar furnaces and gravitational dominance to something fundamentally different. The energy density would have dropped to imperceptible levels. The temperature, despite being only 2.7 degrees above absolute zero today, would have fallen to unimaginably lower values. The cosmic background radiation, that ancient echo of the Big Bang that still permeates space, would be so redshifted and diluted by expansion that its energy would be negligible. Galaxies themselves would have dispersed beyond recognition. The large-scale structure of the universe, those magnificent filaments and sheets of galaxies bound together by gravity, would have dissolved under the relentless expansion driven by dark energy. This is not merely darkness, it is the erasure of the physical frameworks that made galaxies possible. After the last stars extinguish, the universe enters what cosmologists call the degenerate era. The name is apt. What remains is the wreckage of stellar evolution. White dwarfs, neutron stars, black holes, and cold dark planets drifting through an expanding void. White dwarfs are the cooling embers of stars like the Sun. They start hot. Over trillions of years they radiate their stored heat away. Eventually they cool completely, becoming black dwarfs. Objects so cold they emit essentially no light at all. The timescale for this cooling is longer than any star's lifetime. The universe may not yet be old enough for a single black dwarf to exist, but given enough time, every white dwarf becomes one. This era stretches on, trillions upon trillions of years of a universe that is mostly dark, mostly cold, mostly silent. Gravitational interactions between dead stars slowly dissolve the structures galaxies left behind. Objects get ejected from what were once galaxies through the same slow gravitational dynamics that occasionally eject stars even today. The filaments of the cosmic web, already stretched by dark energy, grow sparser still. The universe continues expanding. The temperature of the cosmic background radiation, already just 2.7 degrees above absolute zero today, drops lower and lower as the expansion dilutes even that faint warmth. This is not a universe that looks like anything we recognize. It is a universe of cold, dark objects, separated by distances that are growing, slowly and relentlessly, without any engine remaining to push against the expansion. Then something strange happens. Even the black holes die. Stephen Hawking showed theoretically in 1974 that black holes are not truly permanent. Quantum mechanical effects near the event horizon allow pairs of particles to form from the vacuum, one particle falling inward, one escaping outward as radiation. The black hole slowly loses mass this way. The process is unimaginably slow for large black holes. A black hole with the mass of the Sun would take around 10 to the 67th years to evaporate completely. Supermassive black holes, the kind that sit at the centers of galaxies, containing billions of solar masses, would take something on the order of 10 to the 100th years. A Google years. A number with 100 zeros after it. That is how long it takes before even the most massive black holes are gone. But they do go. Eventually. Each one, as it loses mass, radiates away the last of its energy in a final burst of Hawking radiation. And then it is simply gone. No singularity remaining. No event horizon. Just a fading pulse of radiation dispersing into the void. When the last supermassive black hole evaporates, roughly a Google years into the future, the last large-scale structure in the universe disappears with it. What is left after that point? This is the question physicists call the dark era, and the answer is unsettling in its completeness. The universe at this stage contains a diffuse, cold, expanding gas of photons, electrons, positrons and neutrinos. Protons themselves may eventually decay. The timescale for proton decay, if it happens, is somewhere around 10 to the 34th to 10 to the 40th years, far shorter than the timescale for black hole evaporation. But even if protons are stable, the matter left in the dark era is spread so thin across such enormous volumes that meaningful interactions become statistically negligible. The average distance between particles grows to incomprehensible scales. The temperature everywhere approaches absolute zero. Not exactly zero in principle, but close enough that no thermodynamic gradient of any consequence remains anywhere in the observable universe. This is what heat death means. It is not a temperature. It is the absence of difference. Thermodynamic work requires a gradient, a hot place and a cold place, a high energy state and a low one. The engine of a star runs on the gradient between the hot core and the cold surrounding space. Life runs on the gradient between sunlight and the darkness behind it. When the universe reaches heat death, there are no gradients left. Nowhere is hotter than anywhere else, because everything is equally cold. No reactions run, no chemistry occurs, no structures form, no information is processed anywhere in the universe, because information processing requires change, and change requires energy, and usable energy requires a gradient that no longer exists. The universe does not end. That is the strange part. It continues to exist and to expand. There is no final moment where it stops. It simply reaches a condition from which nothing further can ever happen. Forever. There is no explosion at the end of this story, no dramatic final event, just an asymptotic approach toward absolute stillness, a universe that began 13.8 billion years ago in a state of almost perfect order, a singularity, all matter and energy compressed to a point, and has been moving toward disorder ever since. Stars, planets, galaxies, life, all of it is a local eddy in that flow, a temporary pocket of structure that the laws of physics permitted to exist for a while before the current ran through it. The current always wins. The second law admits no permanent exceptions. The 100 trillion years of starlight are a brief chapter. The Google years of black holes are a long one. But both of them are finite. Both of them end. What follows them does not end, but nothing in what follows them is capable of noticing the difference. Every star that ever burned, every planet that ever formed, every living thing that ever existed anywhere in the universe was a temporary exception to a rule that has been winning since the beginning.